IEI Salem Local Center as Engineers Talk. I would like to invite Engineer S. Loganathan, FIE, Chairman, IEI Salem Local Center, and National Council Member, IEI, to welcome the gathering. Please.
Very good evening to all. So we are organizing continuously the webinar on every Wednesday. So on behalf of IEI, 1 minute. So on behalf of IEI Salem Local Center, I'm happy to welcome all the members and today's chief guest for this wonderful webinar on an important topic. So the title is Operationalizing Net Zero Real-Time Energy Optimization in Automotive Plants Using Digital Twins and AI. So I welcome our chief guest, Engineer Murali Kumar Krishnan, for sparing his wonderful time and sharing his knowledge. Welcome, sir.
Thank you. Thank you very much.
Thanks. So we happily welcome engineering talk committee members and past immediate past chairman, Engineer Tangaraj, Engineer Dr. C. Davamani, immediate honorary secretary, and Dr. Sadish Kumar, present honorary secretary for this 117th webinar meeting organized by the Salem Local Center. So on this occasion, I once again welcome you all. Hope this is a very important topic in the mechanical engineering. So every field has been using the AI technology. So in the mechanical field, especially in the automotive plants, this will enhance the knowledge of the members and students members, those who have joined today's webinar. So I think we will have a wonderful evening with Engineer Murali Kumar Krishnan. So once again, I welcome you, all the members, seniors members, committee members present here for participating in the seminar. So I request Engineer Aramu sir introduce our chief guest.
Okay, Inza, thank you very much for welcoming the gathering. Now it's my pleasure to introduce the chief guest and keynote speaker of today's session, Murali Kumar Krishnan. He did his bachelor's degree in mechanical engineering. He has worked as assistant manager at Renault Nissan Technology and Business Center, India, and technical specialist at HCL Tech. He has over a decade of experience as a PLM and digital manufacturing specialist during transformation projects across automotive and energy sector. He is recognized for digital manufacturing research, which acquired 2 gold medals and certified as a Siemens Team Center professional, showcasing excellence in engineering innovation. He is a trusted mentor and thought leader, passionate about guiding the next generation of engineers in embracing Industry 4.0 and digital thread ecosystems. He has presented 15 plus technical research papers and conducted 15 plus sessions and 600 plus hours of training programs. He has received the following awards and laurels till date. To mention a few, he has received the Young Engineer Award, Dr. M. Vishwesharaya Award, Coal India Award, and so many. With these words of introduction, I would like to invite Engineer Murali Kumar Krishnan, engineering and digital transformation leader and PLM technical specialist, HCL Technologies, Bangalore, to present on the topic real-time energy optimization in automotive plants using digital twins and artificial intelligence. And I request you, sir, over to Murali Krishnan now.
Thank you, sir. Thank you for the very warm welcome and good evening, everyone. And thanks everyone for joining the sessions. And today we are going to discuss about the operational net zero, specifically in the context of automotive manufacturing and how the digital twins and the artificial intelligence, the AI, is being used to optimize the energies in the real time. So before I start, I like to give an important clarification that when we hear about net zero, many people immediately think about some sustainability reports or the carbon reductions or some of the government regulations from the engineering standpoint. But from an engineer standpoint, this net zero is something very different. Like for engineers, the net zero is more about how efficient we convert the energy into value. When I say value, it can be become a vehicle, it can be components, it can be quality throughout the boards, right? So this automotive plants, like the manufacture of a car or any of the vehicles, is one of the most complex and energy intensive systems in the world. And we have using thousands of machines, thousands of robots and compressors, HVAC system to be simultaneously operating, and it will be about operating through the system. So it is not about like operating not about the reducing the uh, energy size. It's not about shutting down the machines. It is like operating how smarter we are and how where the technologies will be using. That's where the digital twins and the AI fundamentals will going to change the game. So yeah, um, yes, everyone discussed. I hope I'm audible. Yeah, before we going forward, hope I'm audible and I'm visible on this camera. Yeah,
Yeah.
thank you, thank you. Yeah. So thanks for the content. So this today agenda and the objective is like it is structured to take everyone in the same journey. Like it can be a students or it can be any engineers or who are the industry professionals and who can be in the part of the professors who are going to be thought of the everyone. So we will begin with the basics, what net zero actually means for manufacturing engineers. Then we will look at how energy can be consumed inside the automotive plants. Please stay on the previous slide. We'll talk about that. And why traditional energy methods are they no longer sufficient. So from there, we will go deep into the digital twins, as it is not only the simulation tool, but as in the operational system, how AI can establish the real-time operations. So we will discuss what is the role of PLM system, especially who are all working with the manufacturing data or in the product structures. Then we will review some few real case studies in India and also in the some global automotive manufacturers, and followed by some of the future trends that going to be the skills the engineers do who can must develop in the system. So let's begin with like what does the net zero mean in the manufacturing? So let's define that net zero in the practical terms. So the net zero is doesn't mean that only the zero energy consumption. This manufacturing will always require an energy, right? So the net zero means like the total net carbon impact of an energy use will be zero over the time. It's not about the immediate past, it's over the time. So for engineers, this can be translated to four action, I can say, like reducing unnecessary energy consumption and to improve the efficiencies of required processes. And also it can be shifted to some of the lower carbon reductions that needed to be finished. And the final part is like the offset what cannot be eliminated. So like what are the things that are not be unavoidable. So the most important part is the first one, like the reduction and the optimization. So in the net zero, it is not about the static target. It is a dynamic. So it cannot be the way, because if you look at the industry, please stay on the previous slide. It can be the production sites and it can be the production mix change. So the net margin will be optimized and it will be meaning to some daily production decisions. It cannot be handled once a year or it's a sustainable report. So it needed the motor energy. So let's look inside how the typical automotive plants will be. So the energy consumption is not evenly distributed, right? So if you talk about example, some of the paint shops will often consumes like 30 to 50% of total plant energy itself. Well, for example, if a plant consumes around 100 kilowatts of power, then nearly 30 to 50 kilowatts will be consumed, particular only with the paint shops. And if you talk about the body shops again, then they are using around thousands of well robots to use for them. That requires some energy. If you talk about the powertrain machines, then it reveals about the high spin loads that needed. And especially if you talk about HVAC system, whether the plant is been in the production or now, it need to be run continuously regardless of any production state. So this is why the key problem will be occur. Like each one of the system is usually optimized individually in the previous part. As of now, as the whole, the production team will optimize the throughput, the maintenance team will optimize the uptime, right? And the utility team will optimize the energy bills and all. But this energy saving is not about the system level operation. It's a system level operation, right? So it's not a departmental like production team will go for the other one will go for the maintenance. It's not the department based. It's like the system level of operations need to be performed. So next slide, please. Yeah. So why the traditional energy management is failing or it's insufficient to handle the industry 4.0? Because the most of the plants is still managing the energy using the historical data. When I say historical data, it using the monthly energy reports, it will be using the energy audits report and some of the driven KPI, what it happened in the past. But this energy waste will be happening in every minute, not even every month. The reports will be generated every month, but it's happening at every minute, right? So the traditional system will not correlate the energy with the production context. It cannot predict the upcoming peaks, how the loads will go up, whether we need the same similar loads in the night. We cannot predict with the existing management system. So we cannot simulate what if this plant goes down, what if the system goes down, what are the energies needed. So this type of predictive actions will not be capable to do with the traditional energy management system that has been. So by the time of a report which identifies as the inefficiencies, the list the loss which has been already occurred. So we need some predictive maintenance system. That's why the reactive energy management, which cannot be supports of the net zero goal, but it will helps to understand how the digital twin and the AI can help you in the future product. So when I say about the products like digital twin or some of the practical explanations. Next slide, please. Yes. So when we enter into digital twin, yeah, many of may not know what is digital twin. It is often understood as like just a 3D model or simulation tools, but in the reality, the digital twins is like same physical component. When I say about there is a core, then you will create a similar digital assemblies and you get the real-time feedbacks and apply on the simulation tool to get their feedback. So this digital twin will often come up with some of the three essential elements, I can say. One is about the virtual model, which is nothing more about the automotive brain. And then the second one will be the live data connections to be received from the physical system to be here. And the third one will be like the feedback mechanism. So it will receive the feedbacks for the optimization and it will fetch into the other system. So in particular to the automotive manufacturing sites, we already using the digital model in the context of industry 4.0 and the 5.0 is evolving. We already be using the digital models during some of the designs and planning. But once the production starts, what will be the play roads? It will be often used as it can be considered as abundant, right? So the true digital twin, I can say it will stay throughout the operations. So it will continuously monitor what is happening on the shop floor, what is happening on the machines, how the energy flows is happening, what is the constraint that has been doing, and what are the performance it need to be do on the particular side. With this one, we'll see how the digital twin across the PLM field. When I say PLM, it's a product lifecycle management. Next slide, please. Yeah. So product lifecycle management is another bit that if you're about to design a product, right from the prototype design to the actual production, to the actual testing, production, until the end life of the products, we can able to manage complaints of one. This is where the PLM becomes the extremely important to conserve on the digital twin across the cycle. So if I say the PLM system, it maybe contains the product structure we used to call as a bill of material, yeah, and we have the process definitions. how the components will be processed through the one, and we have the equipment data and what is the engineering intent particular to this one. So when all these data is connected to MES system, when I say MES, it's a manufacturing execution system. it, it will be communicated to the real-time software system, and we can create a digital thread here. So there is no more the manual interruptions. This all being controlled into the digital threads. So whenever the PLMs and the MES and the OT, when I say OT or IoTs, it's about the interest of the things. The energy consumption will be tracked. So it will be tracked to the design decisions, or it can be tracked to the process choice, or it can be go to the equipment selections, and it can be also be part of the some of the parameters that needed to be in the operating. So with this one, this allows the engineer, the actual plant engineer or any of the engineers, to ask the questions like why this variant consumes more energy, or which process can be increased some more energy demands, right? Or can we use some of the redesigning the components to consume the lower energy? This kind of questions may arrive to the engineers who have been using for the digital systems, because the engineers have all the data that has been put in the like it will help you for the design decisions, or it will help you for to choose the process, or it can be helpful. It can be either way to select the equipment selections, or it can be go for the operation parameter. So this plays a vital role in the digital twin across the plant. So we'll see how it can be improved. Next slide, please. Yeah, this is where my expertise, like how I've been working for in the Siemens products, which is nothing but the team centers and also the multiple systems. The software has been aligned in the Siemens side. So in the modern automotive factories, the digital twins will be not alone the standalone the parts. So they will interact with the PLM system, which is nothing but the team center applications from the Siemens for the engineering data. And it will go for the MES system. It nothing but the op center application from the Siemens goes for and the some of the execution logics. If you talk about the IoT platforms for industry of things, then there is applications called MindSphere. It will go for and the it platforms the sensor data, and to for the any of the analysis system, and for the simulations tool we have the process simulation or the sim center to analyze how the energy has been. So if you look at the complete ecosystem, the Siemens ecosystem, it is interacting with each applications, and it it proves that this digital twin is not about the standalone. This powers has come from the integrations. So it is not about the individual tool, it's about the integrations, and this energy optimizations becomes a closed loop system. Like it will come from the CAD to the PLM to the MES and IoTs, and it go for the simulations, and it prevents back to the design again. So this is a closed loop system rather than some of the manual analysis exercise. This is where the Siemens products will help to establish the digital twin ecosystems in any of the industries. And today we are talking about the automotive industries, and we will see how some of the real case studies that has been helpful. Before we move forward, we'll understand about the A part as well. So next slide, please. Let's understand. We got some rough ideas about the digital twins now, and we'll see how we'll try to understand how the AI in the manufacturing context of fields, right? So the AI is more about often controversial. It's something like a complex system, or it's more, but in manufacturing, it serves as some of the very specific purposes. So it will be good at finding the patterns in the large data sets. Like it gives every 30s of sub-possibilities to give the similar patterns, or certain fastness has been keeping using on this certain level of variance, or it predicts the future behavior, right? So or it will help you to optimize some of the multiple constraints where it has been used on the CAD system during the design, or it will help you to detect any of the anomalies that humans have maybe missed out. So this if you when I say when we hear about the AI, does it replace the man or the manpower? No, it will. AI will does not replace the engineering knowledge, yeah, right? But it augments it. But like, when I say the engineer becomes more conservative, and it will be the more safety limit. So AI will try to explore more optimal solutions within those boundaries. When I say the boundaries, it's not about one of the algorithm. It's of the multiple level of layers. We'll see how this A and the digital manufacturers will fit into the automotive industry, and we will see about some of the case studies of the Indian automotive industries and some of the global automotive industries as well. Next slide, please. Yeah, this is where the AI used for the some of the energy optimizations. Let's look at some of the examples. Like, so this A can able to focus some of the energy demands. Like in the existing manufacturing, we have some of the production schedules, right? And we have the status of the machines. We have the weather conditions. We can able to some behaviors from the historic. So this will forecast what are the load that can be predicted for each number of hours in the particular shift or the particular production cycle. So, and with this existing or with this existing forecast system, it can be help you to optimize the machine to schedules for to avoid some of the peak tariff, like during the time of 3 p.m. to 5 p.m. There is the peak tariff that has been accounts for the most number of energies has been updated. Then the actual engineers will look into this to resolve the problem, how it can be avoid the peak tariffs, how it can be nullified, and how we can reduce the simultaneous high load operations, how we can able to balance the energy cost. So this A will not able to detect some of the abnormal energy consumptions. This will help you to understand, this will detect the abnormal energy consumptions before the mechanical failures occurs. So that's why we call it as a predictive maintenance. These are all the production grade applications, and these are all no going to the experiments or any of the use cases, right? So that's where you can see load forecasting, and there was the production optimizations part, and most importantly for the any of the system, the HVAC, whether the production system this is on the uptime or the full efficiency or 50% efficiency, the HVAC should be operated 24/7 into 365 days. That's where the optimization has come into the places. Next slide, please. We'll see. Yeah. We have seen in some of the loop system that has been the point to be reduced, and to this point we have discussed like the digital twin and some of the AAS and the concepts, and this slide will display about how the net zero is operational minute by minute. Like this is the real automotive plans, and the energy optimization is not a one-time calculation that you know. It is like the continuous feedback loop that has been the part. So the first, the data will be collected from the shop floor or any of the machines, not just the status. It gives about some of the energy meters, what is the temperature sensors, what is the airflows, on what is the utility that has been used. So these all the data will actually happening right now, and but not, that was not planned, right? But as in the secondary version, this real-time data will going for the digital twin. When I say digital twin, this is a virtual system, and it is not about it is not a static. It is the mirror of the current physical state of the plant. It can be a plant, or it can be include some of the, it can be a particular machines or a particular vehicle. So this includes some of the constraints like um what to say some of machine availability, or some of the what is the production orders for today's one or a particular week, or what is the environment condition that can be affected for another one. So this, the first we collected the data from the shop floor, and the second the real-time data that is applied to the digital twin, and the third will be like the A algorithm will come into place. So they didn't ask like what is the ideal in the theory. For example, should we slow down any of the slightly avoids to the peak load when there is in the peak time loads? So should we avoid it? So this will not able to ask the question. This will, the loop will be continuously repeating, and this is like the HVAC reduce has been reduced, or some of the control engineers. So this is the difference. This is the actual difference that you can identify between the monitoring the energies and controlling the energies, right? So, so far in the existing energy management system, we have been monitoring the system, and whenever there is in the break or the down occurs, the production down occurs, we'll be open the troubleshoots on the one. But this is where when the real in this real-time optimizations, the closed loop, we have the identifies between the monitoring the energies and also controlling the total number of energies. This is where the net zero only becomes optimization in the real time. It's not about only the shift ends, it will be optimized in the real time end. Next slide, please. more, yeah. Let's talk about some real scenarios use case that has been in the Indian automotive context, like because the challenge here is very specific. So the India's power grid, we are all aware is it's a very dynamic, and the energy cost, the availability, the carbon intensities is very time to time and day to day within this region, right? So th- the renewable energy we are now seeing about the electric vehicles and the born electrics and everything. So the renewable energy contributions through the changes based on the solars and the wind availability that will contributionally changing. So the most plants today are blinds to this variation. They consume energy based on the fixed schedules, regardless of any of the grid conditions. It's completely based on the fixed schedule. So this creates a particular the two problem that has been arrived, like it increases the higher energy and it increases the carbon emissions than what is necessary on the particular schedule or the particular plan. So this real-time energies intelligence will allow the plants to shift the non-critical process. The critical process will be so it will shift the non-critical process to the low carbon time, and it will avoid the peak time demands, yeah, and it also aligns the productions with the renewable sustainability. Since instead of the fixed schedules, it based on the availability, it will the put it over into some the renewable availability. If I say in the other words, the energy becomes planning parameter. So this energy consumption will become one of the key vital parameters to load, just like how manpower or the material availability. This energy becomes also one of the key parameters particular for the Indian OEM. So this is much essential for the content. We'll see more about some of the any one use case. Next slide, please. We will deep dive into some one shop. We've seen multiple ways. Let's see about some automotive paint shop cases, right? So um, in this focus, we will see how the digital twins and this AI show how the maximum impacts that can be put. So we completely rely on continuous heating, yeah, and the temperature. Let's talk about the challenges. What is the existing on the paint shops that has pieces like they're completely in the continuous heating, and the paint shops require some more energies. Like as we discussed, it needed more than 40% of the total plant energies to foreign the to consume only foreign the paint shops, and it have some of the penalties to be observing, and additionally the paint overrun of the concept of the quality issues. This results the systematically overconsumption of energies for the reworth of work. So what will be the solutions in case the engineer created some of the process level digital twin for the paint ovens? Then the twin model will be like thermal inertia of ovens, and it will use for the curious of behavior, and it go for the circular patterns and detection, and it will go for the takt time. So this how the process of this digital twins of this any of the wine and the AI sensors or the IoTs will help you to resolve the sensors, the temperatures and the airflows of productions one will becomes the part of any of the automotive plants or any of the system that has been the part. So what will be the impact? Obviously, the 50% total on the existing consumptions of the around more than 15 to 20% of the energies will be reductions. This is based on the data that has been shared with Maruti Suzuki, and the carbon deposits of this reductions will be reduced by 10K per ton per year, and this always reduces some of the first time right qualities. So the key insights will be like the energy source will be reduced without reducing any of the quality of the components, and this also make it the decisions based on some of the existing what is it, the temperatures on the this is more about the physics. It's plus that existing data, so it's not of any of the assumptions or any mind calculations. So this is what the operational net zero will be look like on the soft floor over the time. So let's see how the global automotive plants has been using. Next slide, please. Yeah. This in the global, I have taken about the BMW part. So they're the leading manufacturers in the concepts, and they have been from the individual process they have been using for the entire plant, they have been initiated some of the digital factories. They have been created the virtual factories that has been the plan, and this will be using for any of the predictions that has been used and the digital twin that have, so everything has been the virtualized and the digital twin has been entire factors has been implemented. But this means that before a schedule is released, right, so the engineer is already known what are the energies going to depend, what are the load risk, and what is the impact of different schedules of it. So instead of they're asking like, can we produce this many vehicles today or this week, or instead of that they will ask like, what is the most energy and carbon efficient way to produce those vehicles. Instead of they are asking how many vehicles to produce, they will ask how efficient we can able to make those. This is where this approach is where lead to, like, what is the actual reductions one and what is the emissions per vehicles can be controlled. And this this is not about, it's more about acting as the long term planning decision. That is so this is not about only with the automation. This is like intelligent manufacturing system or the next level of automotive plants or any of the system that has been using for the next system. Let's see some of the statistics that has been used. Next slide, please. Yeah. Okay. So this was let's step back. What is the industry that has been the white data? So across the auto, all the automotives and heavy machineries, multiple studies has been researched, and all the white papers has been written. This digital twin enables some of 10 to 30 percentage of energy reductions on the overall plants, and AI-based driven will help you to reduce the peak demands by 15 to 20% or 25%. So on the whole sum, it completely reduce around 50% is the whole one of the reductions that has been integrating by integrating this digital system. Then, yeah, obviously we need some of the initial investments on this making the digital twins, but what is the return of investments? ROI? It obviously, as we seen about the real time investment, it obviously within the 1 to 2 years the results has been consistent because the energy waste is systematic. It is not a random one. Once you model the system correctly, the inefficiency becomes obviously obvious. And the key takeaway here is important for all the engineers and the professionals is like, these gains are not a theoretical, right? They are already being achieved in the production environments, and this this 50% will save a ton. This obviously direct to the profits of the any of the manufacturing industries of the companies that have been already in the place. Moving to the next slide, like what is the design phases we can see? Yeah, one of the most I can say one of the most underestimated fact that has been through. Uh, when we study about the studies, we have talked about the three major operations. Like beyond the operations, we have the more where the most energy decisions are being logged. This includes like the equipment selections and the line layouts. What is the process one? And we can also see in about the some of the process sequencing and the automation level. Like once the plant is built, the operation optimizer can only do so much. It's like this is why the digital twins must start before the productions, not after. After the plan. So this PLM system plays a crucial role by allowing the engineers to compare the existing energy impacts to the design alternative, and it also simulate the long term how the operational behaviors of any of the system or the technologies that has been implemented on the particular automotive plant, and it makes the energies aware that the design decisions has been deployed early. So this is where we the engineers and the automobile particular to the automotive industries, we strongly believe this sustainability becomes like the engineering responsibilities that has been the part than only not particular to the designs one. Yeah. Mm. Next slide, please. Let's see what are the trends that has been going to be in what it can be heading to, like they are moving to self-optimizing factories. So the futures plan based on this existing growth and the one we will adjusting the operation schedules based on the grids that has been one, and we will be optimizing the energies automatically without any of the human interventions. Yeah, and we'll be using AI co-pilots and other GNAs to support the engineering decisions. It can be the design decisions or in the schedule plan or purchasing the new machines considerations, this digital twin will evolve from the decision supports tool into some of the automations tools over the year. So this will be operating within the safeties and qualities boundaries which has been defined by any of the automation engineers or any manufacturing engineers. This will be helpful for the one. And for the students who have been exploring on the manufacturing side, this means that the factories of the future will require the engineers who already ready to understand the system, not just the machines, the whole systems need to be maintained. So that's where the skills that the students or the earlier career engineers should develop, like Net said, please. Let's talk about some of the skills which not only the technology, which are not only enough, the future engineers must combine, like the core engineering fundamentals. Yes, that's where you've been taught in the institutions. And what's the data interpretation skills? Like what is the exact data that IoTs has been occurred and how you can implement on the existing plant. And you try to understand about any of the energy system, and you need the ability to think about like different life cycle phases, like what are the design concepts on the yearly design phases. You will be require only the 10 to 20% subsidies. Maybe in the prototype testing you may need it 5% extra, but during the actual production time, the all the shop floors and every instance, so the energy consumption will be more, and it consumes 50% of total plant energy during the time, and the obviously on the service and the existing phase, nearing the phase. So the most valuable engineers that who can connect is like the design to the production, and production to this energy that has been going for the sustainability. So the tool will change definitely, but the platforms will be evolving. So every system thinks this talk about the most important skills that need the future engineers must evolve on this one and who must be built. Yeah. I think we coming to the near to this session. Next slide, please. Like, what are the key takeaways and what to be remember for this one is like, if there are some three things I can say. Like first, the net zero. It is the operational challenge. It is not about any of the reporting goal or something. So it is the net zero is like the operating challenge. You need to remove the one. And the second is the digital twins. Yes, this provides the visibilities across from the designs to the productions and till the operation. So this provides the visibility, and the AA. The third one is will be the this enables the real time critical optimizations that a human cannot be able to manage alone. So that's where it produces on the 50x or 100x of time improvements over the cycle. When all these three be connected through PLM system on the existing manufacturing systems, this becomes a part of daily productions, and it cannot be a separate initiatives. So these three will be the key takeaways that can be remembered for through the sessions. And yeah, I hope this gives some of the informations about the digital twins and EAs that can be used over in the part. So if you have any of the questions, next slide, please. And yeah, you can please. If anyone have any, or if you have any, if you need more information and details on the digital manufacturing sites or on AA sites that has been implemented, feel free to reach on this email or on my number or even on the LinkedIn page that is on the screen. I'm happy to help. Yeah.
Okay, sir. Thank you very much for your presentation on real-time energy optimization in automotive plants using digital twins and AI. Really, your presentation was very good and useful for us. Thank you, sir. And now I would like to invite Dr. R. Satish Kumar, FIE Honorary Secretary, IEI Salem Local Center, to propose vote of thanks. Please, sir.
Thank you, Arumugam sir. Very good evening to all the members. Thank you for this opportunity to propose vote of thanks. At the outset, I would like to thank our Chairman Engineer S. Loganathan sir for his support and the welcome address. Thank you so much, sir. And Engineer Murali Kumar Krishnan sir, really a wow presentation. Beautifully presented on the topic, need of our topic. Thank you so much for sparing your valuable time with us. Really, this plus. Thank you so much. Thank you so much, sir. I submit my thanks to the engineers talk team for this wonderful arrangement. Dr. K. Tangaraju, sir, immediate post chairman. Dr. C. Davamani, madam, immediate post secretary. Dr. A. Kumaravel, sir, engineer N. Senthil Kumar, sir, engineer Arumugam, sir, and Aynar, sir. Thank you so much for this arrangement. And all the committee members, corporate members, all the student and faculty members, those who have joined for this wonderful session. Everyone, I thank you so much. Thank you all. Thank you. And a special thanks to our Tyagu. Thank you. Thank you so much. Harumu, sir. Thank you, sir.
Okay,
Oh,
sir.
thank you very much.
Thank you very much. Thank you very much for fixing the chief guest. By இன்னைக்கு யாரு இவரு சாரு ரங்கராஜ் சாரா இவரா ஐயனாரா?
I think it's Tangaraj, sir.
So we have to thank special
Yeah,
Rangara sir fixing the
very useful content, sir. Super title, super presentation, sir.
yes.
Super.
Thank you, sir. Thank you
Thank you.
all.
Yeah, thank you so much, sir. Thank you, sir.
Okay, sir. Welcome. Thank you.